On July 16, 1945, at 5:29 a.m., the first atomic bomb detonated in the New Mexico desert. Scientists stood 10 miles away behind protective barriers. The flash was visible for 200 miles. The mushroom cloud rose 40,000 feet. And in that moment, Enrico Fermi did something that seems absurd. He tore up a piece of paper into small fragments, held them at shoulder height, and released them just as the shockwave arrived. The fragments were blown about 2.5 meters. Fermi watched, did some quick mental math, and announced the yield. 20 kilotons. He was right, within 10%. Using falling scraps of paper and mental arithmetic, he calculated the power of the world's first nuclear explosion while it was still happening. But here's what disturbs me. It's not the calculation itself. It's what the calculation reveals about the bomb, about what it actually does, because the atomic bomb is not what you think it is. It's not just a big explosion. It's not just TNT scaled up. It's something fundamentally different. Something that operates on principles most people never learn. And when you understand what Fermi understood, when you see what his calculation actually measured, it changes how you see nuclear weapons, how you see energy, how you see the relationship between matter and destruction. And it's deeply, profoundly disturbing. Let's start with what people think an atomic bomb is. A powerful explosive. Something that releases a lot of energy quickly. Creates a big blast, destroys buildings, kills people. True, but incomplete. Because conventional explosives, like TNT, work by rapid chemical reactions, molecules rearranging, bonds breaking and forming, releasing energy stored in those chemical bonds. A lot of energy, but there's a limit. Chemical bonds only hold so much. Gram TNT releases about 4.6 million joules. That's the chemical limit. You can't get more energy out of chemistry than the bonds contain, but nuclear weapons don't work by chemistry. They work by converting mass directly into energy. Einstein's equation. E equals mc squared. And the speed of light squared is an enormous number, which means a tiny amount of mass converts into an absurd amount of energy. 1 kilogram of meth utilise 90 quadrillion joules. That's about 20 megatons. The energy of the largest thermonuclear weapons ever built, from 1 kilogram. This is not chemistry. This is fundamentally different physics. Now, atomic bombs don't completely convert mass to energy. They're actually incredibly inefficient. The Hiroshima bomb, little boy, contained 64 kilograms of uranium-235, but only about 700 grams of fission. Less than 2%. And of that 700 grams, only about 600 milligrams, less than a gram, was converted to energy. The rest be fission products reactive debris. But that 600 milligrams released 15 kilotons of energy, equivalent to 15,000 tons of TNT, from less than a gram of matter. Think about that. Less than a gram. About the weight of a paperclip, converted to energy, and it destroyed a city. Killed over 100,000 people instantly, injured tens of thousands more. Started fires across 9 square kilometers. Created a shockwave that shattered Windows 16 kilometers away. All from 600 milligrams of mass becoming energy. This is what E equals mc squared means. Matter is frozen energy. Enormous amounts of it. And when you unlock it, the results are apocalyptic. But here's what Fermi was measuring, not the total energy. The shockwave, the blast wave. Because nuclear explosions don't just release energy, they release it in specific ways. And understanding how the energy distributes is critical to understanding what these weapons actually do. A nuclear explosion releases energy in 3 forms. Blast, thermal radiation, and nuclear radiation. The proportions vary depending on the design. But for a typical fission bomb detonated in air, about 50% of the energy goes into the blast wave. About 35% goes into thermal radiation. Light and heat. About 15% goes into nuclear radiation. Gamma rays and neutrons. Each of these kills in different ways. The blast wave crushes buildings and people. The thermal radiation burns flesh and ignites fires. The nuclear radiation destroys cells and causes acute radiation sickness. It's not one weapon. It's 3 weapons in one. And each is deadly in its own way. Before we go further, you need to understand what you're learning here. This is not entertainment. This is knowledge that changes how you see the world. Subscribe to this channel immediately. Hit that like button. Share this video with people who need to understand what nuclear weapons really are. Because most people don't, and that ignorance is dangerous. Let's continue. Fermi's calculation was measuring the blast wave. The shockwave traveling through the air. When a nuclear weapon detonates, it creates a fireball. In the first microsecond, temperatures reach tens of millions of degrees. Hotter than the core of the sun, the fireball expands, compressing the air around it, creating a high-pressure front. A shockwave. This shockwave travels outward at supersonic speeds, initially faster than the speed of sound, and it carries enormous pressure, enough to collapse buildings, rupture lungs, shatter eardrums. And Fermi knew that the distance the shockwave travels before reaching a certain pressure is related to the energy released. He knew the physics, the equations, and he knew that by measuring how far his paper scraps were blown, he could work backward to calculate the yield. It's called a Fermi estimation, an order of magnitude calculation using minimal data, and it worked. Because Fermi understood the underlying physics better than almost anyone. But here's what's disturbing. The calculation is simple. Almost trivial for someone with Fermi's knowledge. You don't need computers. You don't need instruments. Just basic physics and observation. And that simplicity reveals something terrifying. Nuclear weapons are not magic. They're not incomprehensibly complex. They're applied physics. And the physics is well understood. Which means anyone with sufficient knowledge and resources can build one. The hard part isn't the physics. It's getting the fissile material. Uranium-235 or plutonium-239, these materials don't exist in nature, in usable quantities. You have to enrich uranium or breed plutonium in reactors. And that requires industrial-scale facilities, centrifuges, reactors, reprocessing plants. That's the barrier, not knowledge, not design. Materials, and that barrier is eroding. More countries have enrichment technology, more reactors exist. More plutonium is being produced. The knowledge is everywhere. The materials are becoming more accessible, and that's the nightmare scenario. Let me tell you what Fermi knew that most people don't. Nuclear fission is a chain reaction. A neutron hits a uranium-235 nucleus. The nucleus splits, releases energy, and releases more neutrons. 2 or 3. Those neutrons hit other nuclei, cause more fissions, release more neutrons, and so on, exponentially. In a bomb, this happens in microseconds. Each generation of fissions takes about 10 nanoseconds. After 80 generations, you've fissioned a significant fraction of your fuel, total time, less than a microsecond. In that microsecond, trillions of atoms split, release their energy, and the material vaporizes, becomes a fireball. But here's the key. The chain reaction only works if you have enough material. If the mass is too small, neutrons escape before hitting another nucleus. The reaction fizzles. But if you have enough mass, the critical mass, neutrons are likely to cause another fission before escaping. The reaction sustains itself, and you get an explosion. The critical mass for uranium-235 is about 52 kilograms. For plutonium-239, it's about 10 kilograms. These are surprisingly small. A sphere of plutonium the size of a grapefruit is enough. And if you compress it, you can reduce the critical mass further, because compression increases density. More atoms per volume. Neutrons travel shorter distances. More likely to hit a nucleus. This is why modern weapons use implosion. Conventional explosives, arranged around a plutonium core, detonate simultaneously, compress the core, increase density, achieve criticality. Start the chain reaction. It's elegant, efficient, and horrifying, because it means you can make a very powerful weapon with very little material, a few kilograms of plutonium. Some conventional explosives, sophisticated triggering, and you have a device that can destroy a city. Fermi worked on the Manhattan Project. He was there from the beginning. He built the first nuclear reactor in Chicago in 1942, Chicago Pile 1, a stack of graphite blocks and uranium. No cooling system, no shielding. Stabili. And he achieved the first controlled, self-sustaining nuclear chain reaction. December 2nd, 1942, this proved fission could be controlled, could be harnessed. And it led directly to the bomb. Because once you know how to control the reaction, you know how to make it uncontrolled, how to make it explosive. Fermi knew this. He understood the implications. And he helped build the bomb anyway. Why? Because he believed Nazi Germany was working on one. And if they got it first, they'd win the war. Use it to dominate the world. So he rationalized, justified, and worked on the most destructive weapon ever conceived. This is the moral calculus of scientists in wartime. And it's deeply troubling. Now, let's talk about what the bomb actually does to people, because this is what gets sanitized. What gets hidden behind words like yield and kilotons, the thermal radiation. That 35% of the energy released as light and heat. In the first second, it's intense enough to vaporize anything close to ground zero. Human bodies, buildings, everything beyond that. It causes third-degree burns out to several kilometers. Flash burns. The light is so intense it burns exposed skin instantly. People describe shadows. Permanent shadows burned into concrete and stone. The shadow of a person who was vaporized. Only their silhouette remains. Burned into the surface behind them. This happened at Hiroshima. Multiple shadows. People walking, sitting, standing, and then gone. Only their shadows left. This is what thermal radiation does. It burns the image of people into the environment as it destroys them. We're at the halfway point, and I need you to understand something. This is not abstract. This is real. This happened. And it could happen again. Subscribe to this channel right now. Hit that like button. Share this video. Because people need to know what nuclear weapons actually are. What they actually do. Not the sanitized version. The truth. Let's continue. The blast wave, that 50% of the energy. It creates overpressure. The pressure wave compresses air, crushes structures. Achi ground, zero the overpressure is measured in hundreds of pounds per square inch. Enough to pulverize concrete, twist steel. Obliterate everything. Further out, the pressure decreases. But it's still lethal. 5 psi, 5 pounds per square inch over normal atmospheric pressure, is enough to collapse most residential buildings. To kill anyone inside. 10 psi will destroy reinforced concrete structures. And the shockwave doesn't just push, it also pulls. There's an overpressure phase, and then a negative pressure phase. a suction, as air rushes back to fill the void. This creates a double impact: push, then pull. And it tears buildings apart. People too. Internal organs rupture. Lungs collapse. Eardrums burst. This is what the blast wave does. And Fermi was measuring it with scraps of paper. The nuclear radiation, gamma rays and neutrons released during fission. This is what makes nuclear weapons uniquely horrific. Chemical explosives don't poison the environment. Nuclear weapons do. The initial radiation, released in the first minute, is incredibly intense close to the explosion. Lethal doses out to about 2 kilometers for a Hiroshima-sized bomb. People exposed to high doses die within hours or days. Acute radiation syndrome, nausea, vomiting, diarrhea, then a brief recovery, then organ failure, bleeding, infection, death. It's agonizing, and there's no cure. If you get a lethal dose, you die. It's just a matter of time. And the radiation doesn't stop after the initial flash. The fission products, the atoms created when uranium splits, are radioactive. They decay. Release more radiation. For years, decades, centuries, this is fallout. Radioactive dust and debris carried by the wind, settling over vast areas, contaminating soil, water, food, causing cancer, birth defects, genetic damage for generations. Fermi knew all of this. He understood the physics of fission, the energy release, the radiation, the fallout. And he still did the calculation, watched the bomb explode, measured the shockwave, calculated the yield as if it were just another experiment, just another data point. And maybe that's what disturbs me most. The detachment. The ability to separate the physics from the human cost. To see the explosion as a scientific achievement, rather than a humanitarian catastrophe. This is what happens when you spend years working on a problem. When you're surrounded by other scientists doing the same. When the goal becomes abstract. Win the war, beat the Germans. Demonstrate American power. The human suffering becomes secondary, a regrettable but necessary consequence. And you focus on the science, on getting the numbers right, on making it work. Because that's what you can control. That's what you're good at. And it's easier than confronting what you're actually building. After the war, many of the Manhattan Project scientists had crises of conscience. Robert Oppenheimer dat ik Ceremus foute de bewegiet. Now he am become death, the destroyer of worlds. He spent the rest of his life advocating for nuclear arms control, opposing the development of the hydrogen bomb, and was punished for it. His security clearance was revoked. His reputation attacked. Fermi was different. He continued working on nuclear weapons. He was a consultant on the hydrogen bomb project. He didn't express the same level of guilt or regret. Maybe because he was more pragmatic, more focused on the physics than the politics, or maybe because he rationalized differently, saw the bomb as inevitable. If America didn't build it, someone else would. Better to have it and control it than to let others have it exclusively. This is the logic of deterrence. And it's dominated nuclear policy ever since. But here's the problem with deterrence. It assumes rational actors. It assumes no one will use nuclear weapons because the consequences are too terrible. Mutually assured destruction. Mad. If you launch, we launch. Everyone dies. So no one launches. And for 80 years, this has mostly worked. We've had close calls, accidents, miscommunications, but no deliberate nuclear war. Yet, but the logic breaks down in several scenarios. What if an actor doesn't care about retaliation? What if they're suicidal? What if they believe they can limit the response? What if they miscalculate? What if a computer glitches and shows incoming missiles that don't exist? We've had false alarms multiple times. In 1983, a Soviet early warning system detected 5 American ICBMs. The officer on duty, Stanislav Petrov, decided it was a false alarm and didn't report it. He was right. It was a computer error. But if he'd followed protocol, the Soviets would have launched, and we'd be living in a very different world. Or not living at all. Today, 9 countries have nuclear weapons. The United States, Russia, United Kingdom, France, China, India, Pakistan, Israel, North Korea. Together, they have about 13,000 warheads. Most are much more powerful than the Hiroshima bomb. The largest ever tested was the Soviet Tsar Bomba, 50 megatons, 3,300 times more powerful than Hiroshima. The shockwave circled the Earth 3 times. The mushroom cloud rose 64 kilometers, 7 times the height of Everest. The flash was visible 1,000 kilometers away. It shattered windows 900 kilometers away. One bomb, and it was a test, deliberately reduced in yield. The design could have been 100 megatons. They didn't test at full yield because there was no point. 50 megatons was already beyond any conceivable military use. It was a demonstration, a statement. We can destroy anything, anywhere, completely, utterly, and there's nothing you can do to stop us. And this brings us back to Fermi's calculation. What was he measuring? Power, destructive power, the ability to release enormous amounts of energy in a fraction of a second, to vaporize matter, to create shockwaves that flatten cities, to poison the environment for generations. And he calculated it with paper scraps. Because the physics is simple, elegant, beautiful, even, and that's the horror. The same physics that explains stars, that powers the sun, that creates the elements, that makes life possible, also makes weapons that can end civilization. It's not good or evil. It's just physics. E equals mc squared doesn't care how you use it. It doesn't distinguish between a nuclear reactor providing electricity and a nuclear bomb destroying a city. It's the same equation, the same principle, the same conversion of mass to energy, and humans choose how to apply it. So what should we take away from this? First, nuclear weapons are not just bigger bombs, they're qualitatively different. They release energy from mass itself. They create radiation that persists. They have effects that span generations. Second, the physics is understood. The barrier to building them is materials, not knowledge. And that barrier is eroding. Third, deterrence is fragile. It relies on rationality and luck, and we've been lucky so far, but luck runs out. Fourth, scientists bear responsibility, not just for discovering physics, but for how it's applied. Fermi and others made choices, built the bomb, justified it, and those choices shaped history. And finally, this knowledge matters, not to scare you, but to inform you, because nuclear weapons still exist, thousands of them, on hair trigger alert, ready to launch within minutes. And most people don't think about them, don't understand them, don't realize how close we've come to using them, and that ignorance is dangerous. Fermi died in 1954, cancer, possibly caused by radiation exposure from his decades of work with radioactive materials. He was 53. He never saw the full extent of nuclear proliferation, never saw the Cold War arms race peak at 70,000 warheads, never saw the fall of the Soviet Union and the partial disarmament, never saw the current tensions, the new arms race, the breakdown of treaties. He died believing deterrence would work, that rational actors wouldn't use these weapons, And so far, he's been right. But every day we rely on that rationality is a day we're betting civilization on human restraint, and humans are not always rational. History is full of mistakes, miscalculations, accidents, and with nuclear weapons, one mistake is enough. If this video changed how you see nuclear weapons, how you see the responsibility of scientists, how you see the fragility of our current situation, then you need to act. Subscribe to this channel right now. Hit that like button. Share this video with everyone. Because this knowledge is too important to stay hidden, too important to be forgotten. Fermi calculated the power of the first atomic bomb with paper scraps and mental math. And what he measured was not just energy. It was the beginning of an era where humanity has the power to destroy itself. And we need to remember that. We need to understand it. We need to grapple with it. Because the alternative is complacency. And complacency with nuclear weapons is a path to extinction. So subscribe, share, and I'll see you in the next video, where we'll continue exploring the truths that change how you see the world.